In this video, we are going to be talking about Chapter 4, Water, Waves, and Tides, and how important that is to all the living organisms in the water. Here's the key concepts that we are going to go over, and you can check those later if you need to. Marine organisms are actually about 70 to 80% water, which is pretty watery, especially compared to us on land that are only about 66% water. Water is an excellent solvent, meaning it can dissolve things into it. It has a really high boiling point and a high freezing point. It is actually denser in its liquid form, which is awesome because it means that ice can float. This is really significant when you're talking about glaciers, being able to float on top of the water and not sink down. And it has lots of other applications for the cycling of water. And then it also helps organisms that are in the water. It has a certain level of buoyancy, so they can kind of regulate using fat and air to maintain like a certain distance in the water column. And it's a great medium for chemical reactions. Here's a good video by Mark Moverman with a solution formation animation. It kind of is a good animation talking about how water can break up different solutes that are put into it. So, water has a certain polarity, and what that means is that water actually has two hydrogens attached to it and one oxygen attached to it. And the hydrogens have a positive charge on the two sides, and the oxygen has a negative charge. So, you can almost, like in my mind, I kind of think of water as being slightly like magnetized almost, where it has a slight pull to other water molecules that are around it, because the negative and the positive sides will actually kind of attach to each other. And this actually helps so many different, or makes up so many different properties of water that make it really cool. So here's a video by Ricochet Science, properties of water, where they go over that a little bit more. Also, when water freezes, it actually makes this amazing lattice where you see like all the different ions kind of line up due to their polarity, which is really cool. So having a high boiling point for the water, so water doesn't get overly hot and boil really quickly, which actually would cause a lot of problems for living things. And the reason why you need to add a lot of heat to water before it breaks down is because of those little positive and negative bonds. If you think about a few magnets, and if they're stronger magnets, how much energy it takes to kind of pull them apart. So if you think of water almost being magnetized like that, you need to put in a lot of energy to pull those little bonds apart and get it into a vapor form. Also, it has a high freezing point, and it has that because it can fall into its crystal lattice shape pretty easily and go to a frozen state. So water is actually a solvent of a lot of different things, especially polar ions. So when something else is polar, meaning it has like a positive and negative charge to it, so say like table salt, it will actually use those properties to kind of almost magnetize or pull to it and separate the solute out. But that also means that nonpolar molecules like oils and fats, water will not react with those, and those will stay separate. I'm sure you've heard like oil and water don't mix, but it's because one is polar and one is not, that happens. So here's a video by What's Up Dude, the structure of water, that you can check out. Water also has some other important properties like its cohesion. That means it attaches to other water molecules, and you can kind of see that in the GIF where it kind of magnetizes towards each other. It also has adhesion, where it will pull up the side of of something, like it'll hold up to the side of your glass or something like that, where it'll cling onto the side surfaces of things. And that also contributes to it having a high surface tension. So the reason why this spider can walk on top of the water is because it's using the surface tension of the water, the clinginess of the water molecules that are holding it together, and it's light enough weight and it's spreading out its weight enough that it can actually walk on top. When I worked and researched in Borneo, we would have to walk through really deep water sometimes, and I'd have a number of these spiders just fall down my rain boots as I walked along in this water. And in Guatemala, I got to see basilisk lizards that are like often called the Jesus lizard because they can run across the water because of this surface tension. As long as they get going fast enough, they can make it across, which is really cool. So, where this plays into importance is in the ocean is especially between sand molecules, like larger sediment, um, pieces of sediment, there will be different living things, and those living things depend on water. And so, having this water that will move through and kind of cling to other water molecules and stay in little pockets makes it so that those living things there can have water, which brings them life. Here's a video by Professor Dave Explains Viscosity, Cohesive and Adhesive Forces, Surface Tension, and Capillary Action that you can check out for more information on that. So water can also hold a lot of heat, so that helps it to maintain a really constant temperature. That becomes super important in the winter and even in the summer, where the water between the winter and the summer months doesn't change its temperature nearly as much as the air above the water, because the water has such a high specific heat thermal capacity. As light travels through water, it travels through differently based on the energy in the wavelength. So, red, orange, and yellow are very low energy lights and they don't penetrate very far into the water. Blue really dominates and spreads out really wide and ends up so all the water ends up looking really blue, although in some areas where you have a lot of sediment and plankton, it can actually kind of appear pretty green. One interesting application of this, since the reds, orange, and yellows don't make it very deep in the water, one time I was thrown in as a scuba diver in really deep water into some lava rock, and I cut up my thigh really badly. And I really didn't care about the pain of the thigh because I was super interested that my blood coming off of my thigh was actually appearing green. It just, all this green blood was coming out of my leg. And I just found that incredibly interesting. I did not have a camera, but I was able to find a video from YouTube that shows another diver who slightly cut his finger, not nearly as dramatic of a cut, but it's by Tim Powell, Scuba Diving and Green Blood. And you can see what that looks like. And the blood looks green. It's not faked, because the red, orange, and yellow stop so high in the water column that it appears green. So salt actually has a really good, or I'm sorry, water actually has a really good ability to maintain a neutral pH. So the pH of water is actually at a 7, although our ocean water is slightly basic. And so it's the opposite. Basic is being like the opposite of a little acidic, although the ocean is slowly, you'll hear, is getting more acidic because it's trending towards the acidic side instead of staying on the basic side like it should. Additionally, salt water is composed of different minerals in it. So here's a breakdown of what's in there: chloride, sodium, sulfate, magnesium, calcium, potassium, and bicarbonate. But additionally, there's a lot of trace elements in our oceans that different organisms end up taking up into their tissues. So kelp specifically, I put a gif of that there, has the ability to pull iodine in, which is a very trace element in the ocean, into its tissues and concentrate iodine. So if you go and buy a lot of iodine supplements, a lot of the times that you will see it's been harvested from sea kelp. if you were able to sort the water and the salt in the ocean and separate them all out, you would see that the salt pile is only 3.5% of the total um, solution that's there. But still, if you think about all of the ocean water, 3.5% salt is so much. And that affects different ocean organisms, because some organisms want to be more salty than the ocean, some want to be in harmony with it, and some want to be less salty than the ocean. And so organisms have to have different mechanisms for maintaining the amount of salt in their bodies that they want. So this is a video by BBC Earth Unplugged, Why is the Sea Salty? And this is just a really interesting video about that. But basically the salt, the amount of salt in the water will change drastically based on all of these different factors like evaporation, precipitation, freezing, thawing, runoff from the land. All of those things will affect it. And here's another picture image of what that cycling looks like and how that can change. Up here's an interesting picture. I actually got to visit the Dead Sea and you go swim, and everyone famously likes to swim and float in the Dead Sea because you float really, really easily. But the Dead Sea it's really warm water and it evaporates, so it gets very, very salty, so much so that the water spray will actually collect the salt on the seawall to the sides. So interesting with salt water, there's different gases that dissolve into the water and fit in between the water molecules. So oxygen is something that's given off by plants in photosynthesis, and CO2 is from things that respirate or breathe out. Carbon dioxide, it's a byproduct of respiration. Well, interestingly, there's different amounts of gases in ocean water. So specifically for nitrogen, there's a lot more in the air than there is in the ocean water. And in oxygen, for oxygen though, it's opposite. There's actually more oxygen in the ocean water than there is in our air. And I know that seems hard to believe, but that's actually true. And it kind of got cut off here, but our CO2 in the air is actually like about 0.04, whereas in the ocean, it's about 15% of the gas in the ocean is actually CO2, making the ocean what is called a carbon sink, where it takes on a lot of CO2 for us. So when we are putting a lot of CO2 in the atmosphere, we think it's all just going in the atmosphere, but a lot of that is sinking down into the ocean. And that's problematic because when it enters our ocean, it actually breaks up into carbonic acid, and carbonic acid does further break down. But that is the process that is really acidifying our ocean. Our oceans do have bicarbonate in there that help the ocean maintain a neutral pH by giving up their hydrogens or taking in hydrogens as necessary to make a neutral solution. But the problem is the rate that we're putting in the CO2 in the oceans. It's becoming problematic for them. This is a video by Bozeman Science, Ocean Acidification, that talks about that in a little more depth. So every day the oceans, just like the whole rest of the earth, is receiving a ton of energy from the sun in the form of heat. And near the equator, it's receiving the most energy from the sun, and near the poles, it receives less of that energy. A lot of the energy is reflected or off of Earth altogether and is sent back into space, but some of it will actually cycle and stay near our Earth because of the greenhouse effect. The greenhouse effect, in a lot of ways, has a bad reputation just because it's part of what is warming our earth, is having a lot of different things in the air like methane and CO2 and things that are causing the air to keep more and more heat from the sun. That's what's causing global warming. But in many ways, this buffer these greenhouse gases around our Earth do keep us at a really good temperature and keep us at a really nice constant temperature because of how they trap the sun and cause the greenhouse effect. What you don't want to have happen is that getting out of control and causing too much heat to stay near our Earth's surface. So as the sun comes down to the Earth, much of it will be absorbed by the atmosphere, by land, and by water, but some of it will be radiated and reflected back up. About 47% of the incoming solar radiation is actually absorbed by the Earth's surface on a daily basis. So the sea temperatures can vary every day, and it can vary seasonally, and that's affected by energy absorption that's coming from different currents or the atmosphere. And it also has seasonal variation based on the tilt of the Earth and the sun's rays. So, overall, though, you're going to see that if you look at the map of ocean sea temperatures, it's not a surprise that near the equator, you're going to have the most ocean warmth there. And then as you climb north or south in this picture, if these are like in degrees C, you're going up about, every time you go up or down, you're increasing or you're decreasing by about 5 degrees C, which is pretty significant until you get all the way up to the Arctics or get all the way down to Antarctica, which is actually very, very cold. That's where you're going to have the coldest water, more than even in the Arctics. So wind moves by currents, and it does that in a few different ways, but one of the ways is just by temperature. So if you look at this cool GIF of somebody lighting a match here, you see that the air around the match gets very warm very quickly. But what's interesting is it doesn't just spread out all of its heat with the surrounding air. The hottest air kind of stays in a bubble and starts moving upwards because heat rises as part of that current. And the cooler air stays down below. So watch this heat bubble as it starts to move up. You'll actually see that it goes up, and it's forced by cooler air coming down below is forcing it up even more. And this cycling happens every day, especially in coastal communities. During the day, the land will heat up a lot, and as it does that, it will force the hotter air up and the cooler air will come down. But in the evening, the wind reverses direction where the water over the ocean is warmer, so it comes up and the land cool air gets cooled down. So winds are also very affected by the Coriolis effect, and not just winds, but currents in the water. And we'll talk about how that happens. But the Coriolis effect is the spinning of the Earth that affects the northern and the southern hemisphere differently. So in the northern hemisphere, these wind currents will spin clockwise, whereas in the southern hemisphere, it will spin counterclockwise. And this is a video by Atlas Pro called the Coriolis Effect Explained that shows you some great visuals of what that looks like. So you get the wind spinning in different directions, and you get various cells that move in those directions that we can kind of categorize. And one of them is the trade winds that occur near the equator. And near the equator, they will move both from the northern hemisphere and the southern hemisphere. The westerlies are winds that move from the west to the east, and they happen just near the 60 degrees north and 60 degrees south sign. They move from the west to the east. And then you also have the polar easterlies that move from the east to the west, are the polar easterlies. They'll also, because of the wind moving in these directions, there will be some air that needs to just go straight up from the earth. And it's almost like a perpendicular movement that goes from the earth straight up into the sky. And because of that, those areas are kind of dead zones for like ancient sailors and things. If you're trying to sail across there, the wind isn't moving side to side, it's moving straight up into the air. So that doesn't help you in sailing. Those areas are called the doldrums right here on the equator line, or you can have the horse latitudes that are 30 degrees north or about 30 degrees south. And here's a video by Keith Meldal called Global Atmospheric Circulation that you can check out to see a visualization of what that looks like. So there's different currents heading across our oceans, and here's an awesome TED Ed how do oceans work that I really like. The western bound currents are not very productive as far as having a lot of nutrients, but they move a lot of water and add a lot of oxygen to the ocean for ocean creatures to use up. So there's actually a unit for measuring the flow of ocean water called a spheredrup. And a spheredrup is actually moving 1 million cubic meters of water per second. Picture that, 1 million cubic meters of water per second is one unit of measurement. Well, the Gulf Stream has a flow of moving at 55 spheredrups. That is crazy to me to move that quickly. So our Gulf Stream is down by like the lower eastern United States. Then you have eastern boundary currents, which move really slowly, but they carry a ton of much needed nutrients with them and are very, very productive, which is really cool. Not as much oxygen, but a ton of nutrients. And then you actually will have these little transverse currents that are not moving east or west. They're kind of moving up or down in between the east-west currents. So here's just a map of what that looks like across the world. So the energy from surface winds gets transferred lower to deeper water. But you have to kind of picture it that if you have wind blowing across the ocean in this direction, so here's the force of the wind in this graphic, and it's moving across the surface of the ocean. As that energy moves downward and gets transferred deeper and deeper, it's going to have less and less of an effect. So the water near the surface is the most affected by the wind, and then deeper, even though some of that energy is transferred, it's going to kind of dissipate by the time it goes deeper. But another weird thing that happens in this scenario is that as the wind is blowing across the water, you're also going to have the earth spinning, and you're going to end up getting these circular currents. So while the wind pushed the surface water straight, because the earth is spinning over time, this is slowly going to shift the energy in a circular pattern as it moves down through the water. So this is actually a phenomenon called Ekman transport. And here's a really cool video by Science Primer, Surface Currents, the Ekman Spiral, and Ekman Transport that I recommend you check out because it's an interesting explanation of how that works. So water has different densities, which is the mass of a substance in a given volume. Pure water is going to have a 1 gram per centimeter cubed, whereas salt water is slightly more dense than that. And this really, really matters as far as how water mixes. So this is a really cool video by Ocean Climate at UOL, Density, Layering, and Stratification in the Ocean. This is about 1 to 2 minutes, but really worth seeing what this looks like visually. He has very less dense water on top, more dense water on the bottom, and then he took these two waters and he mixed them in a separate tank here and put in some red dye. And when he pulls out the partition, you'll see the red dye water that's in the middle of these two will actually sort itself in between, because you would think that water just mixes all the time, but the different densities actually separate themselves out. But that's not the only way water separates itself out. It also has thermoclines where it'll separate based on temperature, where it'll have the warmest water on the top, the coldest water on the bottom. It also separates by salt amounts, called the halocline, where it'll have very salty water deep down below and less salty water at the top. And then you can actually have a what's called the pycnocline, where water actually gets more dense the deeper it is down into the ocean. And that can all also be affected by seasonal thermoclines. So seasonal thermoclines look like this. Let's start out in the summer. If in the summer you can picture that the surface water of the ocean is at its warmest. The sun is shining and it gets really warm. And the colder water is down below, and in between is a thermocline. And you can actually physically feel this when you dive into lakes, or even if you're in the ocean water and dive low enough, you can feel these temperature changes. Well, fall comes along, and let's say it's a really cold fall. So it actually cools off the surface temperature water. So it's actually colder than the water down below. Because it is colder, it will actually dive down, and that's where this darker blue water is. It starts to dive down underneath the warmer water below, and it causes the warmer water to come up and start to have this mixing called an isopycnal. And so that is where in the winter it is usually like more like the same temperature throughout. And then in the spring it starts to warm up on the surface area again. And so the water on top is warmer, the colder water is down below, and it lasts that way through the summer until that seasonal change again. This is really, really good for mixing nutrients and has so many positive effects for moving oxygenated water, and has a big effect on the living things in the ocean. So it's not a big surprise that the warmest water, surface water on the planet, when you look at this map, is going to be near the equator, and it's going to get cooler as you move north or south, with the coldest being at the poles. But that also means that it's the most dense water at the poles and the least dense water towards the equators. So this is what this looks like on the chart here, that you might see something like this, that a normal water column has the very blue, meaning the colder water at the bottom, and then it has the warmer water on top. Overturn is when the cold water is on top, it'll start to overturn or head down to the bottom, forcing the warmer water up. And then a isopycnal is where the water is perfectly mixed for the time being, but it will always go and sort itself out again later. So this upwelling and downwelling is so important, that as things die and nutrients come off of land, that those extra nutrients from dead plants or decaying matter do fall to the bottom of the ocean, where they're further decomposed and broken down. But then it's very important to bring those nutrients back up to the top to be used again. This is a video by Hakai, What is Upwelling, that shows you more about that process. So there's also some deep, deep water circulation that goes on, with the Antarctic having the coldest water, and that cold, very cold Antarctic dense water will eventually move up towards the opposite pole at the Arctics. But I want to show you another very interesting one to me in the Mediterranean. The Mediterranean Sea has very, very warm water because it's shallow and it's in the middle of a desert. But that also makes it really, really, really salty. Well, usually warm water is not that salty. So you have very salty water, which would normally be at the bottom of the ocean, but it's also very warm, which would normally be at the top. So as the Mediterranean Sea feeds through this very, very narrow place called the Strait of Gibraltar and heads out into the Atlantic, do you think it stays on top with the warm water, Or do you think it dives down with the salty water at the bottom? So the answer, it has to pick. You would almost think it goes in the middle or something, but it does not. It actually is so dense because of how much salt it is that the salt wins out and it dives very, very deep into the Atlantic. But weird because it has a totally different density than the rest of the deep water because it's actually warm, salty water instead of cold, salty water. So it has a different density. It actually maintains its own layer and stays separate from the other ocean water. So you can actually find this very warm and very salty Mediterranean seawater like thousands of miles away from the Mediterranean Sea. It has still maintained its own layer and its distinctive properties from the rest of the space, which is totally interesting. So, waves are actually formed a few different ways, but we're going to talk about wind in this case. So if the wind goes and hits the water, it will transfer some of its energy to the water and cause it to have a little bit of a wave. And waves are classified by having a crest and a trough, which is this lower area, and the crest is like this little corner top area. A wavelength is from one crest all the way to the next crest. You can see what the wavelength is of the waves. And when we talk about waves, we talk about what is the generating force, what caused this wave to happen. Well, in this case, it's the wind, but you can also have something like an earthquake or a boat or something like that can also cause a wave. The restoring force of a wave is what eventually causes the wave to calm down and stop. Sometimes it can be gravity or surface tension or the Coriolis effect. This is a good video by Concerning Reality, How Do Waves Work, that I would recommend checking out. But waves, as they come to shore, if you have shallow water waves, as these waves come to the shore and the shallow water starts to hit the land, you can see that the land is curving up and it's forcing this wave to put more and more of its energy into less and less water. Out here it was really deep, but here it's really shallow. So all of that energy gets transferred to the wave and it causes the wave to have the back of side of the wave starts to overtake the front side of the wave, making what's called a breaker or a breaking wave onto the beach. And that was what makes these fun little surfing waves that I'm sure you've played with in on your summers. The deep water though, deep water waves are not as affected by the bottom because it never gets that shallow to make that happen. So this is kind of plays into how tsunamis work, that you can sometimes have very large earthquakes out in the ocean that transfer a lot of their energy to the ocean water. Well, the energy in the ocean water where it's really deep doesn't seem like a big deal, but as that energy transfers closer and closer and closer to land, those waves from those big seismic earthquakes can make tremendously large tsunami like waves. So, this is a cool video by Ted Ed, How Tsunamis Work, that I recommend checking out. So, tides are changing the level of the water along the coastlines. And a lot of times you can have, well, you have different forces that work on them. So, in this, I want you to look at this picture and have it divided three different ways. So, here in this middle section, you have the earth in the darker blue and the water in the lighter blue on the outside. You can see the water's not very deep in this middle section, and it is labeled low tide. That's because there's two different forces working on this water and they're working in different directions. So the tides or the water is getting pulled to different spaces. It's getting pushed this way and pushed that way, which makes a low tide here. So one force is the centrifugal force. That means the earth's spinning, it's just swinging the water off to one side. And the other force working on the other side is the moon, and the moon having a gravitational force. So centrifugal force can help cause a high tide, and the direction and movement or the placement of the moon in relation to the earth can also cause a high tide. Um, so with that, you can actually have two distinctive types of tides called the spring and the neap tides. So a spring tide is when the moon and the earth and the sun, and it can be on this side or this side for the moon, but the moon and the earth and the sun are generally in alignment. You're going to have what's called the spring tide, which makes a little bit of a bigger tide because it's really getting pulled to one side or the other. But a much smaller tide is called a neap tide. And a neap tide makes the ocean pretty flat all over. And that's because you have the moon, the earth, and the sun kind of at right angles to each other at this 90-degree angle. So basically, the moon is pulling this way, and then the earth is here, and the sun's pulling that way, which spreads the water pretty evenly everywhere. So other things that affect the tides can be like the continent shape or the shape of the ocean floor or the rotating earth. So you would think that everywhere has the same tides as you, but that's not really the case. So a diurnal tide is a place that has one high tide and one low tide, and every day the high tide water line is about the same as the low water tide line, and it's pretty predictable, and everybody's fine. That's in places like Mobile, Alabama. They have a diurnal tide. Then you can have a much more complicated slide called a semi-diurnal tide. This is where you have two high tides and two low tides every single day. It's going up and down and up and down, the high and the low tide, and it's moving a lot. One example of this would be like Cape Cod on the east coast of the United States. But then there's an even more complicated version, like what you see in California, because we like to keep it complicated out here. But in the California tides, you have two high tides and two low tides every day, but they're different heights throughout the day. So you'll have one high tide, but then you'll have a higher high tide. Then you'll have one low tide, but then a super low tide every single day. So you have two highs, two lows, and they're all different heights, which keeps it interesting. If you want to check out tidal patterns, here's a map that shows you ones like the mixed diurnal tides, or like on our east coast of the United States, or on the west coast of the United States, or the east coast of the United States. You'll have semi-diurnal tides, and you can check out, like here in the Gulf Stream, you'll have the diurnal tides. So I hope you gained a greater appreciation for our water waves and tides, and understand maybe a little bit better how they are affecting our living things as well.